Bonjour. Welcome to Wahsa Distance Education Center's radio Zoom classes. This is MBF3C, grade 11 college math, and I am the teacher, Bronwyn Slade. If you'd like to participate live today, you can call the Wahsa studio at 1-800-465-7144 or 737-4017. You can listen on the radio at 91.9 FM and also on the television at Bell Express View channel 972. You are always welcome to join me live through the Zoom link, which is available both from me, your teacher, and also your DEC. Our classes are scheduled from 10 to 11 in the morning and through Monday through Thursday. We are now in our third week of our 9-week course. You should start to be thinking about submitting work for marking at this point. So a reminder of the support questions, the ones with the little pencil icon, are not for marking. They are practice problems, and you decide which ones to do and how many of them, whichever ones feel best for you. If you're understanding something, feel free to skip ones. You don't have to do them all just because they're there. The answers are in the back of your booklet, so check your work just to make sure you're on the right track. This is really a useful tool. The key questions, the ones with a little key icon, are the mark questions. You do all of them. Make sure you're handing them all in. Show all of your work, your steps, and your thinking, so I can know what it is that you know. And also, if you are struggling with something, then I get more information and am able to actually support you. So how do you submit your work for marking? Well, there's 3 methods. The first is to scan your work and send electronically. If you have a device, you can scan your completed work through it. Most the Apple devices have the Notes app, and the Android devices have the Google Drive app. These are both free apps that come with scan functions that are pretty much just point and click. So it's pretty straightforward. If you do need some support about how to use these scanning functions, my YouTube channel has tech tutorial videos that will walk you through how to use them. It's, again, fairly straightforward, and I go through it step by step. If you need more support, feel free to ask, and I'm happy to help you. Or if you just need to take pictures, that's your only option, you can do that too. Scanning just makes the files a little bit smaller and easier to manage, but pictures are totally fine. Then send them to me through email at studentwork@nnec.on.ca and CC it to bronwyn.slate@nnec.on.ca. Or you can also send it to me through Facebook Messenger, where my name is B. Slate Wahsa. The second method is to drop your work off in Sioux Lookout. We have an outdoor mailbox at 74 Front Street. We are the bright red building next to the post office and have a small white mailbox next to our side entrance. So just stick your work in there and I'll get it back to you as soon as I can. Finally, the third method is to hand your work into your DEC. Your DEC can either send your work through the Express or fax it to 807-737-1732 or toll-free fax to 1-800-463-7852. Students can also fax in their work, but if you're going to do that, just give us a heads up so we know to expect it and it doesn't get lost in the shuffle. If you'd like to connect with me through social media, both my YouTube and my Facebook are under the name B. Slate Wahsa. If you friend me on Facebook and subscribe to my YouTube channel, you'll get notifications every time I upload one of our new lessons. All of our radio Zoom classes are recorded and I upload them shortly after broadcasting. So it is a really easy way to access all of our videos and if you need to review something. Also, there are short videos that explain common errors and confusing concepts. So that is a useful place to go as well if you're struggling. Instead of just doing a general search online, this narrows it down a little bit. Math is an incredibly visual subject, so it's super important that you access the videos to set yourself up for the most success. Just listening to the audio is only going to give you a small portion of the chance to understand what it is that we're doing. So joining me live on the Zoom, whether or not you want to talk to me is fine. You don't have to, no worries. Or if you watching the videos on YouTube after airing, doing that whatever works for you is also totally fine. If you would prefer, or that doesn't work for you, and you need a copy of the videos, then let me know and I'm happy to send you a copy of the videos so you still get the full experience. If you have any questions or concerns, please reach out and contact me. My email address is bronwyn.slate@nnec.on.ca. My Facebook is bslatewasa. Give me a call at 807-737-1488, extension 2209, or toll free at 1-800-667-3703. My office hours are Monday through Friday, 8 a.m. to 2 p.m., though I teach from 9 until 11, so that is not a good time to try to get a hold of me. Lesson 5 is where we're at. We're wrapping up Unit 1 today, and this is simple exponential equations. Our learning goals for today are that you'll be able to sketch by hand the graphs of exponential functions. And then you will also understand the key properties of exponential functions. You know that you've met these learning goals through the success criteria, which are that you can visualize and sketch exponential graphs, you can explain how to identify an exponential equation, and you can explain the similarities and differences between exponential growth and decay. Students are always wondering when they're going to use this in real life. Well, we are discovering how the world around us makes sense. So this is one of the things where patterning really shows up, and it's important to be able to look at the whole world and figure out how it makes sense in order to thrive in it. So this is a skill that we're developing through this course. But first, let's activate our brain with some mental math. I don't believe in Mad Math Minutes. They cause stress and anxiety in more students than not, and that is not a useful tool for learning. So instead, we work on developing strategies that are about friendly numbers and comfort and confidence, that use strategies that make sense to you and are logical. Our question today is 84 times 15, and we're going to be using the strategy of breaking factors into smaller factors. So 84 and 15 are two factors. We're multiplying them together to find our product. But I don't know what 84 times 15 is at all. So what I'm going to do is I'm going to break it into smaller factors that multiply together. So 15 is equal to 3 times 5. So that might be useful information to know. And 84, well, I can see that if I cut 84 in half, I get 42. So 42 times 2 is equal to 84. So this is still all going to be the same. So I could do 42 times 2 times 3 times 5, and I'd get the same answer as 84 times 15. Still, this 42 is not friendly for me, so I'm going to try to break that up into even smaller factors. So 42, I know is, I again see that 21 times 2 could be something, and even further, 21 I can see is 3 times 7. So now, this is when it's kind of tricky in terms of thinking, well, what am I actually multiplying to be the same? So 3 times 7 times 2 times 2 times 3 times 5 is going to be the same as 84 times 15. Now, you don't have to break it down all the way down here. If somewhere along the way this makes sense to you, that feels comfortable, then that's totally fine. You do what feels best for you. So I'm going to then, with multiplication, it's commutative, so we can rearrange these things to numbers that feel friendlier. And I'm going to say, well, 2 times 5 is 10. So 10 is a pretty friendly number to multiply things by. So I'm going to multiply the 2 times 5 and make it a 10. And then I am going to say, well, 3 times 3 is 9. And that leaves me with the 7 and the 2 to multiply together. So I know that 9 times 7 is 63. And then I can double 63 because doubling is something that's fairly comfortable. So that's 126. And then I times it by 10 is 1,260. So 84 times 15 is 1,260. So again, this might be not the most useful strategy for you. Depends on the situation, the numbers. You also don't need to break it down all the way to do all these steps, but it does help in terms of figuring out how to do it mentally, to move the numbers around and make them friendlier so that you can maybe use those tools that you have to do the multiplication. All right, what prior learning do we need to know today for our exponential lesson? I just want to make sure that we understand exponential growth. And we're going to look at the example of doubling to make sure that we know what we're talking about when we're talking about exponential growth. So it means that every time we increase our time by 1, so whether it's 1 hour, 1 day, 1 month, that doesn't matter. So we're increasing by 1, the amount of our stuff is doubling. So let's look at this by an organizational chart. So as time increases, what happens to our amount? So first as we start with, so time hasn't increased at all. We are just at our baseline and we have 1 thing. So as we increase our time by 1, that means now we have 2 because we went from 1 thing and we doubled it, we now have 2. So we increase our time by 1, so now our time is 2 and we are doubling what we had on day 1 or on time 1. So we had 2 on time 1, so now we have 4 on time 2. We move forward 1 more time, we're now at time 3, we double what we had on time 2, so now we have 8. And with time 4, we double what we had on time 3, which was 8, so now we have 16. So you can see really, really quickly, we go from 1 on time 0, we've moved 4 spaces away from that, and now we have 16, which is significantly more. And we can just keep going, but we run out of space on my screen. It just goes up so quickly. So then we also want to understand exponential decay. So we're going to use the example of 1/2 as we look at this. And it means that for every time increase again, but this time our amount cuts in half. So instead of getting bigger, we're going to be getting smaller. So once again, let's look at our comparison of our time to amount. So on day 1, we're going to start with a big amount just to help us see this. So we're going to start with 16 on our day 0 at our beginning, our baseline. Then on day 1, we've cut half of that amount away. And so that amount cutting away means that now we have only 8 left. For day 2, we again cut half the amount. So half the amount of 8 is 4. So now we only have 4 left. Day 3, we cut half the amount that we had on day 2, which was 4. So now we have 2 left. Day 4, cut the amount in half. We now have 1 left. So you can see once again with exponential decay, we get smaller really quickly. Just with those 4 time increases, we've now gone from 16 down to 1, and we continue, but then we're going to be talking about half circles and quarter circles, and it just gets smaller and smaller and smaller, which is hard to see. So exponential growth and decay change really, really quickly. All right, so now that we understand what it means to be exponential, let's look at what new concepts we're going to be learning today. So this exponential growth is something that is all around us. Whether or not it is a perfect curve, it is a pattern that shows up all sorts of places in our world. So for example, the percentage of the initial price of a car versus how many kilometers it has been driven is a exponential decay. So you can see, doesn't matter what kind of car we're talking about. Yes, they happen at slightly different rates, slightly different amounts, but they still follow this curve of dropping dramatically at the beginning. First, we start and we're dropping really, really quickly at the beginning, and then that slows down over time, but we lose a lot of value initially at the beginning. If we look at the number of smartphone users over the history, so it was very gradual in terms of people who use smartphones. It started off slowly, and then in about 2010, Android really took off in terms of folks using, and though it's not exactly a perfect curve, we can see it really increases. Smartphones for Apple also increase, but it's at a slower rate. So this is still exponential, it's just that it's a slower exponential growth, which we're gonna look at a little bit about how that happens. The forgetting curve, which we've talked about in terms of how we retain information, how we learn information and keep it in our head, is also a decay. We forget things quickly and in an exponential way. So really quickly at the beginning, and then that slows off, peters off. And referring back to the beginning of the coronavirus, the Corona-19 virus, at the beginning, it was slow for the first couple of days, but then after it just went faster and faster and faster. And so the significant amount, like these numbers, so this was a beginning of March in 2020, so right at the beginning of something that was happening worldwide. At the beginning, it was like a couple of thousand, and then by 10 days, we were at 10,000, and then by 15 days, we were at 15,000, and then by 20 days, we're now at 30,000, and at 25 days, now we're at 60,000. So you can see, though it started off slowly, it then really, really quickly increased really, really rapidly. And that is why it was so concerning, was because it was just spreading so quickly. So exponential functions show up in all sorts of patterns around us. So let's understand a little bit deeper, and this is on page 30 of your IL booklet. As we've already noticed, it's a mathematical model that describes either growth or decay. This is the formula: y equals a times b to the exponent x. Exponential hopefully would have triggered that we're talking about exponents, that this is where a variable is. So the base is our b. It is any positive number, but except for 1, because if you have a base of 1, then it doesn't matter how much you change your exponent x. You have an x of 1,000,000, it's still 1 times itself 1,000,000 times, it's still going to be 1. So your base can't be 1. Then this a is called a scalar, and it's any non-zero number. So this is how it changes from being something that is really, really steep or much more gradual. So it's still an exponential shape, but it shifts how the diagram looks. Then x is our input number, the number that we control. So how often our cycles are happening. And y is our output number, which is our result. Same as always before. So the key is exponential functions always have a variable in the exponent. That is why they are called exponential functions. So that is where our variable is. That is the part that is changing that we're comparing. So for example, d is equal to 8.25 to the exponent t, exponential. Y equals 2 to the exponent x minus 3 plus 1, exponential. C equals -6 times 0.33 to the exponent n, exponential. All of the exponents have a variable. Some non-examples, things that are not exponential functions: y equals x squared plus 5x plus 13. Though we have exponents and we have variables, the exponents are numbers. P equals 128 times I minus 93. Here we don't have any variables in our exponents, not an exponential function. This last one, W equals x to the 4th, y z to the cubed plus x to the -2, y plus y to the 0.5z. Here that we have lots of different variables, we have lots of different exponents. Again, none of these terms have an exponent have a variable in exponent, and therefore it is not an exponential function. So there are several properties that all exponential functions share. And this is on page 30 of your IELTS booklet. So when b is greater than 1, when your base is bigger than 1, this is exponential growth. You are getting your b is 1, you're getting bigger. So it looks like this. As you can see on my graph, there's no numbers. It doesn't matter what our numbers are. It's always going to have roughly this shape where we are increasing as we move further to the right. Our function is increasing. It's getting higher and higher on our y-axis. If exponential or decay is when our base is between 0 and 1. So when it is a fraction or a decimal between 0 and 1. So then it looks like this. It's a reflection. So we still have that same curve, but now as we move further to the right, we are getting smaller and smaller and smaller. When our scalar is equal to 1, all of our exponential graphs will go through the point 0, 1. So they will cross our y-axis at 1, because when our x is 0, that means our base, no matter what, becomes 1, right? Because anything's exponent 0 is 1. And then if we're multiplying it by 1, we're still 1. So here you can see I have 6 different exponential functions that all have a value of 1, a scalar of 1. Doesn't matter if I'm increasing or decreasing, they all go through that 1 point. And the other thing to note is that there is no x-intercept. It is not possible for y to be equal to 0. So it's hard to see what I'm talking about, but our lines are never going to cross the x-intercept. We're never going to go from positive to negative. The only way that we have negative values is if we have a reflection, is if our a value is negative and we're reflecting everything down in the negatives, but then it still won't cross the x-axis unless it's shifted. Again, we don't need to pay attention to those details. So in our parent function form, we always are getting closer and closer and closer and closer and closer to the x-axis, but never crossing it. And those are standard for all exponential functions in that parent form. If we shift them around like we did with the parabolas, then things can change, but there still always will be we call it an asymptote, a place that we never cross. Now you can do the support questions on page 32, questions 1 and 2. In exponential functions, there's a few that are really, really common that happen a lot in general society that are sort of touch points to understand. So we're going to look at these ones a little bit more detail to help us understand the possibilities. And though there are infinite number of different exponential functions, these are ones that are just really, really common. So we're going to look at doubling time and half-lives, as these are just really common in the scientific and general world. So first, doubling time. This is, like we did before, the time that it takes for a quantity to double in size. So the formula for this is P equals P0 times 2 to the exponent t divided by d. What do those variables mean? So P represents our final quantity, how much we're going to have at the end. P sub 0 represents the initial quantity. So this, having a subscript of 0, is a mathematical notation for the initial amount of something. And then T represents the time, and D represents the doubling time. So how long it takes for whatever we're talking about to double. The base 2 indicates that it's doubling. So if it was a 3, then it would be tripling. If it was a base 10, then it would be increasing by 10 times the amount each time. So that is the part that this is the example that we're looking at doubling time. So that's why the base is 2. But you could change that base to any other number and the others would then be talking about, the D would be representing the amount of time it takes to triple if it was tripling time, or the amount of time it takes to increase by a factor of 10. So doubling is just simpler to just look at this one. Half-life is the time it takes for a quantity to decay to half its original amount. And the formula is m equals m sub 0 times 1/2 to the exponent t divided by h. Similarly, m represents the final quantity. M sub 0 represents the initial quantity, so how much we start with. T represents the time. H represents the half-life, so how long it takes for this, whatever it is we're talking about, to cut in half, to be at half its size. And the base is a half, indicates that it's half-life. Similarly, again, we could have, if it was a third, quarter, whatever, 100th, it would then tell us how much it indicates that fraction that we're talking about. Okay, so let's practice. Let's look at what this means and have a little bit of real life connection. So, number one, the E. coli is a very harmful type of bacteria that can be found in meats. That is, if it's stored improperly or handled. So probably you've heard of E. coli, people getting really sick. It's part of food poisoning, people getting really sick. So the relation n equals n sub 0 times 2 to the exponent t divided by 20 estimates the number of E. coli, which is the n, of an initial sample, which is n sub 0, of bacteria after t minutes at 37 degrees Celsius, which is body temperature, under optimal conditions. So those are just some scientific caveats. They don't affect the math that we're going to be doing. So part A, what is the doubling time of E. coli? So because we're talking, our time is in minutes, t minutes, this 20, this D, we don't have a D, we have a T, but that means that it's 20 minutes. So it takes 20 minutes for E. coli to double the amount of bacteria in wherever they are. That is very quick. So if a sample of E. coli contains 5,000 bacteria, how many will there be after 1 hour? So we need our T to be in minutes, and this time it says 1 hour. So first we need to think about, okay, well, 1 hour is 60 minutes. So our T is going to be 60. So we need to make sure that our variables line up based on the definitions that were given in our question. So then let's use our formula. So we have n is equal to n sub 0 times 2 to the exponent t over 20. So that is equal to 5,000 is our initial amount times 2 to the exponent 60 divided by 20. So then let's put this in our calculator. 5,000 times 2. Remember, our exponent button is a to the exponent b. And then you need to figure out for your calculator if you need to put it in brackets, or if you can just if you can do the division in your exponent. So that is equal to 40,000. So in 1 hour, bacteria goes from being 5,000 to 40,000 E. coli bacteria. This is why E. coli spreads really quickly and is really concerning. So if a sample of E. coli contains 1,000 bacteria, how many will there be after 1 day? So again, our time we need to think about, because how many minutes are in 1 day? So we have 24 hours times how many, 24 hours are in 1 day, times 60, because there's 60 minutes in 1 hour. So if we do that, well, 60 times 20, 60 times 2 is going to be 120. So 60 times 20 is going to be 1,020. 60 times 4 is going to be 240. So that's going to be 1,440 minutes are in 1 day. And see how I've sort of written this over to the side, close to where I'm talking about time. I could label it something a little bit differently, but because I have the T, I know that this is what I'm figuring out. This helps me understand what it is, keep my information organized. So let's use our formula again. We have n equals n sub 0 times 2 to the exponent t divided by 20, which is equal to 1,000 this time. So a smaller amount of bacteria times 2 to the exponent 1,440 divided by 20. So using our calculator, you need to have a scientific calculator generally to use these exponents. So if you some calculator apps that you have for phones don't have exponents. So let me know if that's the case, if that's what you have, and we can figure out. So this is 4.72 times 10 to the exponent 24. 4.72 times 10 to the exponent 24. You may or may not remember scientific notation, but this means that we move this decimal 24 places to the right. So that means that we'd have 22 zeros. 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So this is a number that's so big, I don't even know how to quantify it. I don't have a name for it. But that is how, again, how one small bit of E. coli, 1,000 bacteria, which they're really small, sucks, but after only one day have increased by this amount because they double every 20 minutes. So it just, in one day, we go from being 1 hour to being like, yeah, it just skyrockets, right? So this is the importance of understanding exponential functions. Okay, so example 2. The relation t equals 190 times 1/2 to the exponent t over 10 can be used to determine the length of time, t, in hours, that milk of a certain fat content will remain fresh. T is the storage temperature in degrees Celsius. So what is a freshness half-life of milk? So how long can milk stay fresh at this temperature? So the half milk is equal to, so this half-life is this space here, right? This is where H is. So T10, which time is in hours, so 10 hours. It's the same. So let's graph the relation. So I have used Desmos to do this just to move things along quickly. But you can see I've picked various values for x, including a negative x. We can have negative x values, right? We're just not going to get any negative y values. And then I have done every then I've shown every 4. So then here we can see on our, if I graph it again using Desmos, let's move this over here. I've plotted all these points. So they're hard, they have lots of decimals, they're really in between. So using something like a graphing software can help us get a really smooth curve. If you don't do this and you're doing it by hand, that's totally fine. It doesn't need to be super, super precise. So even if you round it to whole numbers and then you're doing approximations, it's okay. You're still going to get roughly the same shape if you're doing it correctly. So we can see that this is exponential decay, which is what we were expecting. So how long will milk keep fresh at 22 degrees Celsius or at 4 degrees Celsius? So this is different because here we are given capital T. So we're given our storage temperature is equal to 22, and our storage temperature is equal to 4. And we're trying to find our little t for how long it'll be fresh at those temperatures. But we can still do this. So what we're going to do is we're going to say, well, T, we're going to replace capital T, we're going to replace with 22 is equal to 190 times a half to the exponent T over 10. So 100 and I'm trying to think, we've done this. Have we done this before? Or do we do this later? We're going to look at we haven't done this before using a calculation system. We will do that later. So instead, because we don't have the tools that we need, we're going to use our graph. And we've graphed this, and now we're going to zoom in and look and say, okay, well, if we're comparing time is our horizontal variable and temperature is our vertical variable. So if we look at 22 degrees Celsius here, oh no, it's going to be, because this is 2, 4, 6, 8, 10. Sorry, this is 22 degrees Celsius. So we're going to follow this line across. And see where it hits our function. And then we're going to go down, and this doesn't land on a line, and that's fine. But it's going to tell us approximately. So, and it's approximately 31 hours. So you can keep, so 22 degrees is generally room temperature. We can keep milk on the counter at 22 degrees, and it will last for 31 hours. Okay. So that's just over a day. So if you leave your milk out overnight at room temperature, it's probably fine in the morning. If it's at 4 degrees Celsius, which is the temperature of a fridge, generally, so that's down here. So again, we look across our line. And we see it goes here, down to here, and this is 56. So it's good for 56 hours in the fridge, which is 2.5 days. So this says a certain fat content that we don't know how much fat is in this. So we don't know if it's pasteurized or not. So we don't know exactly, but because most milk lasts longer than 56 hours in the fridge. But that gives us a bit of information. We can see how it, using your graph, we can figure that information out. We don't have the tools to do it using algebra yet. All right, let's do a few more practice problems. Number 1, complete the table of values using of x between -3 and 3 inclusive. So here we have, oops, didn't mean to do that. We're going to do a table of values where we're going to go from -3, -2, -1, 0, 1, 2, 3, and we're going to have 10 to the exponent -3. Remember, we have a negative exponent, so that means it's 1 over 10 to the exponent 3, which is 1 over 10 times 10 times 10, which is 1,000. So it's 1 over 1,000, so it's 1,000. 10 to the exponent negative 2 is equal to 1 over 10 squared, which is equal to 1 over 100. 10 to the exponent negative 1 is 1 over 10 to the exponent 1, which is 1/10. 10 to the exponent 0, we know is 1. 10 to the exponent 1, we know is 10. 10 squared is 100. 10 cubed, 10 to the exponent 3 is 1,000. Okay, so that is the table of values for y equals 10 to the exponent x. If we do the same for b, we have y equals 1 over 10 to the exponent x. So we're still going to make a table of values. So x, we're still going to do from -3, -2, -1, 0, 1, 2, 3. And we're going to do 1 over 10 to the exponent -3. Well, we already have our base is already a fraction. So remember that if we have a negative exponent, our base is already a fraction. That means we flip that and we have a positive exponent. So our fraction 1 over 10 becomes 10 over 1, which is just 10 to the exponent 3, which is 1,000. So 1 over 10 to the exponent -2 is 10 squared, which is 100. 1 over 10 to the exponent -1, which is 10 to the exponent 1, which is 10. 1 over 10 to the exponent 0 is equal to 1. 1 over 10 to the exponent 1 is equal to 1 over 10. 1 over 10 to the exponent 2 is equal to 1 over 1 squared over 10 squared, right? Is how it works. Well, 1 squared over is still 1. 10 squared is 100. And 1 over 10 to the exponent 3 is, well, 1 to the exponent 3 is still going to be 1. So it's 1 over 10 to the exponent 3, which is 1 over 1,000. So there we go. Sorry that my things are a little squished. So number 2, how are the values in the table related? So if we look, they are the same values, but in opposite order. And that is how they are related when if you look at our bases, we have 10 as our first base and 1 over 10 as our second base. And so the values are the same, but our orders are opposite. One is they're increasing or decreasing by the same amount, but one is increasing, where y equals a to the exponent 10 is increasing, it's growth, whereas b, y equals 1/10 to the exponent x is decreasing, is decay, but it's happening at the same rate. All right, so then the next question says to graph both, and I'm going to use Desmos to do that. It didn't link, so we're gonna go Desmos, because Desmos not only has a scientific calculator, it also has a graphing calculator, which I haven't mentioned before. So we can put in our functions, and so you do y equals 10 to the exponent x, and then we do y equals 1 divided by 10 to the exponent x. A tricky thing is that when you have a fraction in your base, it's going to, if you want your x to be on the whole fraction, so you need to move your cursor. So whether or not you're on a smartphone and you touch to move it, or you use the arrows like I'm doing, or you use a mouse to click, you need to move it from down here being in your base of, in the denominator of your base to outside, and then you can put your brackets, and then you can put your exponent. So that's just something to pay attention to. So you can see we we're right that our values, our two graphs look exactly the same, but reflected. And our red line here is growing, and our blue line here is decaying, but otherwise they look exactly the same. And that's what you can use Desmos to help you graph. It's totally fine, or to check your graph if you need to. So then, how are the graphs related? So they are mirror images of each other. With y equals 10 to the x being growth, and y equals 1/10 to the x being decay. And that is that. Practice question 5, identify the type of growth, linear, quadratic, or exponential, illustrated by each graph, and justify your answers. So justify your answers says, tell us why. How do you know? So part A is exponential. And we know because it has no x-intercept, doesn't cross your x-axis, and it grows quickly. Right, part B is a straight line, so that means it's linear. Part C is a parabola, so parabola is quadratic. So, and you might not know the word parabola, you might not remember, but you might say that it has a U shape. And that's how you know that it's quadratic. D, again, we're not crossing the x-intercept, we're getting closer and closer, but we're not crossing. And we are getting more and more negative quicker, but it's still an exponential, it's just that now we're reflected in the bottom. So it's still exponential, it still follows the same shape, even though we're decreasing, even though we're getting more negative. So I'm going to say growing negatively quickly, which is a weird concept. I get it, but that's what's happening. And then E is, again, a straight line. It's linear. So being able to recognize these different types of functions that we've talked about is super useful when you're analyzing information. And finally, number 6, identify which graph represents each relation, justify your response. So we have graphs A, B, C, and D, which I've drawn through Desmos. They're different, these different colors. A is green, B is purple, C is blue, and D is red. And then we have part A, which is y equals 0.1 to the exponent x, part B, which is y equals 2 to the exponent x, which part C, which is y equals 1/2 to the exponent x, and part D, which is y equals 10 to the exponent x. So how I would do this is I would say, well, I know that having a base bigger than 1 is going to be growth. So part B, y equals 2 to the exponent x, and part D, y equals 10 to the exponent x, are both going to be growth because they both have bases that are greater than 1. So they have to be either C or D because those are both my growth. Now, which one's going to grow faster? Well, if I'm multiplying 2 times 2 times 2 times 2, and then multiplying 10 times 10 times 10 times 10, well, the 10, the one with a base 10 is going to grow faster. So that means it's going to be steeper. So that means that it is line C, and that leaves part B to be line D, because I am growing, still exponential growth, but I'm growing slower, and therefore I have a smaller base. So that means that I look at my other two, which would be my decay, was what I would expect, because those are my two lines that are left, and I both are between 0 and 1. I have 0.1 as one base and 1/2 as the other base. So again, that makes sense. So they're both decay. So they're both A or B. That makes sense. And then similarly, well, 0.1 is the same as 1/10 to the x. So I know that 1/10 should be a reflection of 10 to the x, and 1/2 to the x should be a reflection of 2 to the x. So I can look and say, okay, well, B is the reflection of C. So that means that 1/10 to the x is going to be B, and A looks like the reflection of D. So 1/2 is going to be line A. I also can think about the fact that 1/10 times 1 times 1 times 1/10 is going to be steeper. My line is going to be steeper. It's going to get smaller faster, just the same way that we looked at the growth. And that's how you can, I haven't written down my justification, but we talked it through just for the sake of time. Okay, let's quickly consolidate before we're out of time. So for lesson 5, we have done solving exponential equations. So y equals a to the exponent bx, where b is our base, and it's any positive number except for 1. And a is our scalar, which is any non-zero number. If it's 0, then that erases everything, right? So that doesn't work. If b is greater than 1, we have exponential growth, like we just looked at. If b is between 0 and 1, we have exponential decay. If a is equal to 1, so when a is equal to 1, then all of our exponential graphs go through 0, 1. They hit our our y-intercept at 1. And if they never have a y, the number equals 0, so we never have an x-intercept, they never cross the x-axis. So these are all qualities of exponential functions, properties, I guess. So hopefully you can now visualize and sketch exponential graphs. They are hard to do exact because the numbers are a little bit tricky, but sketching is fine. You can explain how to identify an exponential equation. We know how to look at an equation and recognize it. And you can explain the similarities and differences between exponential growth and decay. So we've just done that a few times of how are they similar and how are they different. And that's important to understand. If you have any questions, as always, please reach out and connect with me. I'm here to support you. Call me at the office at 807-737-1488, extension 2209, or toll free 1-800-667-3703. Send me an email at bronwyn.slate@nnec.on.ca, or a Facebook message at bslate-wahsa. Also, all of our lessons are up, as well as previous years that I've taught this course on my YouTube channel under a playlist. MBF3C is where all the resources are going to be there to help you out with your needs. Thank you so much for joining me today. I hope you have a lovely day. Miigwech.